If we want to find the composition of two functions that are both defined symbolically, and we're not given a specific input, then we again start by translating f circle g to mean f composed with g. We write it as f of g of x. And we again can start with the inner function and work our way out. So g of x I'm going to replace with this g of x definition right here. So g of x I'll replace with 1 over x minus 9. But I'm going to build up the rest of this around it. It's still in parentheses. It is still as input to the function f. Now I think about my function f. F is the function that takes its input and squares it. The input to this function is the whole expression 1 over x minus 9. So this is equal to the whole input 1 over x minus 9 quantity squared. And I could simplify this a little bit by at least squaring the 1, which gets me just 1, and then keeping the x minus 9 in parentheses squared. We don't need to multiply out that denominator because generally factored denominators are easier to work with. So my function f composed with g of x is equal to 1 over x minus 9 quantity squared. And my domain is just the set of all x such that x is not equal to 9. 9 is the only value that would make this denominator equal to 0. So let's now follow this same process in reverse to find g composed with f of x. You can pause the video and try this on your own, or if you're not sure, you can follow along still. I'm going to again start by writing this as g of f of x. And then I will again start on the inside and work my way out. So f of x is the same thing as x squared, and this is still in parentheses, still as input to the function g. The function g has an x in the denominator. All I need to do here is wherever I have an x in the formula for g, I will put x squared instead. That will get me g of x squared. So this function is 1 over x squared minus 9. And to find that domain, I again need to find the values that make the denominator equal to 0. So this denominator, x squared minus 9, I could solve this equation. We could think of it as a not equal 0. I could solve this by factoring or by square root. I'll go ahead and just go with square root, remembering to consider both the positive and negative square roots. So we can see that this domain is the set of all x such that x is not equal to plus or minus 3. So we can see that the order of composition really does matter. It affected the function itself, it affected the domain also. So this is not a commutative operation. Evaluating a composition of functions from a graph, we again start by just writing this according to the definition. F composed with g of 1 is the same thing as f of g of 1, and I again work my way from the inside out. So g of 1 I will look at first. If x is equal to 1 and I trace over to the graph of g, I see that I get negative 1. And this is still inside the parentheses and inside the input to the function f. Now I'm going to negative 1 on the x-axis and tracing to the function f to see what f of negative 1 is. and I get 2. So it's a sequential process again, just like it was with that numeric example that we started with. So go ahead and try g composed with g of -4. Yes, you can compose a function with itself. And g composed with f of 3. Maybe pause the video and try those and then compare to what I get. G of -4 is equal to 0 because -4 is an x-intercept of the function g. And then g of 0, here's 0, tracing to the function g, we get -2. And g of f of 3, again starting from the inside, here is 3, trace over to the function f, looks like we're getting this 2. Start over again at 2, trace to the function g. This appears to be an x-intercept of the function g, and therefore this is equal to 0.